Know why, but maybe they have the old version. Yeah. I don't know why, but I have the old version of the slides here, but that's fine, I guess. Got that.
That really don't want to meet. So that's Robert there. And that, and that's Doug. There are a few more people.
What is the team that I'm in?
What does it stand for?
It's the Greek god from knowledge.
Mm.
Sorry, Egypt.
Okay, that's not. Only the Mediterranean.
The Egyptian god for knowledge. I'm not gonna.
I don't know the Egyptian spelling.
Yeah, there's no weird. Actually, the spelling you may know. The pronunciation that you didn't know.
Well, hieroglyphs, I don't know.
Yeah. Okay, they have two, just like the Japanese, they have two alphabets. One was a phonetic one was a kanji-like one without any characters.
Okay.
That's why we know how to pronounce their heroes, but we don't know how to pronounce their language.
Okay.
The language is what is written in the kanji, in the Chinese characterized things. The phonetic stuff is used for the main values in the tools. The phonetic stuff they know only because of actually the Rosetta Stone and a few other communications with other countries.
Yeah,
and there you can then derive it from Latin and other languages or Greek or whatever it was.
Yeah, so they guessed a few pronunciations because of some names of pharaohs, right?
For sure.
Yeah. Okay, so maybe we can start. Can you hear me well online? I guess so.
Wait, I need to turn this on then again. Okay, now they can talk.
Okay, well, I hope you can hear me well online. I checked before and it was fine. So let's hope for that. All right.
Look at.
Okay. No, I think it's fine.
All right, if they don't complain.
Yeah, if they don't complain, that's fine. So welcome everyone to this MIAI distinguished lecture. It is my pleasure to welcome and introduce Jan Peters, who is a full professor at TU Darmstadt. Jan is also a research fellow and like the head of the research department on systems AI and robot learning from DFKI, and he's a founding research faculty of the Hessian AI Research Center. I will not describe Jan's achievements for long because it would take a seminar by itself. So, I think it's more interesting to hear to what he has to say. But I wanted to highlight a few things. For instance, that Jan received an award for his PhD thesis. It was the Dick Volst Best 2007 US PhD thesis runner-up award. After his PhD, he joined Max Planck as a senior researcher for at least, I think, 5 or 6 years.
It was full-time there for 4 years, a little, 4.5 years.
Okay.
And then I was part-time for another 10 years.
All right. And then, of course, after that, he joined TU Darmstadt. On top of the PhD award, he received the IEEE Robotics and Automation Society's Early Career Award and the International Neural Network Society's Young Investigator Award, as I said, among many others. And on top of his exceptional scientific contributions, some of them will be described today, Jan has also significantly contributed to the community by, for instance, co-founding the IEEE Robotics and Automation Society's Technical Committee on Robot Learning, which got an award for the most active committee of the society. He's also an associate editor of IEEE Transactions on Robotics and Journal of Machine Learning Research. He has been area chair at many top-tier conferences, and he has been program co-chair at Curl and Humanoids, which is a lot of work altogether. So thanks a lot for all this effort. And with no further ado, please join me and welcome Jan, that will give a talk on inductive bias in reinforcement learning for robotics. Thanks.
All right, thank you very much. Thanks a lot for that kind introduction. Can you guys all hear me? Do I need to speak louder? Okay. Alrighty. So I'm going today start things with a movie. I did my PhD 8 Miles from Hollywood, and this is one of my favorite movies because it actually should make every single roboticist embarrassed. This was in 1969, right when the first industrial robots came out, and they directly made a movie saying like, okay, this is going to be what you have in your home. You'll see in a second that this is a bit unrealistic to have it in your home, since, well, that's quite a monster, which we have there. But they were so cocky back then that they said, okay, it's quite natural. Jetson-like a mate in your home will be possible. Pretty crazy when you think about it, that the principles used in this video is hacked up by highly paid engineers. That is the exact same principles which today most of industrial robots still using, right? Direct trajectories, stiff PID control laws with a gravity compensation in there at maximum, and every single object placed up to a few millimeter accuracy. And if one of the objects was placed in the wrong way, then the whole program would fail. Now, back then, you needed an expensive engineer. The robot cost several millions. The compute power was less than the typical iPhone, actually less than the typical watch we have today. But at the same time, it cost millions. And well, today you could ask the average high school student, you just give them a frontal robot that a regular desk PC, and you can hack this thing up. But the principles have changed so little for most of industry. And for Europe, this is devastating, right? I mean, we have an overaging population. We actually need robots that can be instructed in a better way. And I think that's really the crucial part here. Now, let me fast forward through the rest of the video, which is even more embarrassing because it shows.
Was it delegated or was it?
No, it was completely programmed. So just wire points, just PD control. Really, I think the only part where they cheated was the part where the bottle of champagne was opened, obviously. Everything else was hand programmed. I think they had to refilm a few things several times so that it really worked out. But they really made this as a demo presenting the future. It was about to happen. Now, we see from the housewife staying at home drinking champagne while the guy goes to work in a suit, how anachronistic it really is, and how much we've moved on and everything else except for the most important part, the intelligence of the robots. And so the big question we should ask ourselves is, well, why don't we have such robots? And well, I think we need to ask the question the other way around. We need to ask the question the way around that we say, where have robots been successful? And well, on the big commercial scale, we obviously know the car industry. I mean, before Germany decided to destroy its car industry, this was the only reason why there were cars being made in Germany. I'm pretty sure the same holds true for France, Italy, and all of the other European countries. That only due to really, really good robotic technology, we have been keeping these jobs in Europe. And otherwise, they would have been moved as hand manufacturing, well, to wherever you can still pay for hand manufacturing, which is very few countries these days anymore. So, but here you actually see very precisely the same technology at work as in the video before. Everything is placed up to 100 micrometer accuracy and executed it precisely. Then Well, what are the other two examples? Well, the lawnmower robot, where we all know there's a wire in the ground. And well, the Roomba, where everyone who has ever bought one knows the first thing you do when you buy one is you rearrange your furniture so that it doesn't get stuck, like this one here. So in other words, we're typically successful in robotics when we adapt our environment to the robots. What we really need to do in the future is we need to adapt our robots to the tasks. When I got into robotics, saying such things was kind of like violating a religious dogma. When I was an undergrad student, I worked at DLR and I said, oh, we will need learning in the future. They said, oh, no, you won't need learning in the future. And despite that, for adapting robots to tasks, learning is kind of the most natural framework ever. Now, things have changed a lot. I think the recent successes from we all have watched the Atari games, MIAI gym stuff, all of the stuff coming out of DeepMind, that it seems to be quite natural that we should use reinforcement learning and generally machine learning in order to instruct our robots. But at the same time, this is not so trivial. So since when you look at it, well, the reason why classical robotics is still so powerful, it's used everywhere, is, well, simply classical robot engineers are really good at their job. Right? It's the most expensive part in a factory these days is the robot engineer programming the desired trajectory. The robots themselves, they're cheap like that. But we need to beat these guys in order, if we want to make learning and turn learning into the standard solution. We need to be at least as good as the classical robot engineer. And at the same time, whenever you start talking to machine learning, core machine learning people, they'd say, oh, you should just use giant amounts of data and every problem is easy. In robotics, data is expensive. Since data requires that the robot engineer does extra hours and the robot does extra hours, and then you haven't produced anything at that point. So in other words, data is super expensive. And when you say this thing to, well, again, classical, normal, a non-robot machine learning person, the next thing they're going to say to you is, oh, well, but in this case, you should learn in a simulator. And again, now as a robot learning person, you need to reply to this. If you have a simulator that is so good that you can do learning in it, why don't you do planning? Planning, we know how to do very, very well. And we can go for much, much more complex things with planning than we can do by learning. It's just that our simulators are typically not so good that we can just take an off-the-shelf planner with a bad simulator and get a good solution. And then, of course, things break, things wear out. So our robot learning solution has to actually cope with non-stationarity. And yes.
Yeah, well, I fully agree with you. Maybe we could add that planning, which is offline process, is worse than you say because it does not take into account sensors.
Sure, but you could do online replanning too.
Right? Yeah, but it's
the computing power we have today is, after all, if you need 2 nuclear power stations, you see this OpenAI video where it just was moving this cube in the hand. It took 2 nuclear power stations for 2 hours to produce all the energy they need for their cluster. I think we can all agree if you're willing to put that into learning, with a quarter of that we can do online replanning as well, right? So if our models are good enough for doing that.
A successful story that you have not mentioned is robotic assisted surgery. I think it's
there's a ton more of successful stories.
Okay.
Big problem with surgery was obviously that you need to fix the bones, and then planning works actually quite perfectly there. Just the damage of keeping the bones in place is actually the key reason why it isn't, why non-teleoperated surgery hasn't taken over. Since I mean, the hip bone operations that are much better with the planning system than they are done by any surgeon. Just keeping what I don't know how that bone is called. Keeping that one in place, you need to do things which were so drastic. That is the reason why
We don't have it everywhere, but we only have the teleoperated solutions these days. But yeah, that's a big, there's many things I won't mention. All right, then next, generalization. It's often impossible. So the hope of learning that we can, once we learn, I don't know, let's say table tennis, we can do hockey, I don't know, every other sport immediately, is actually not that trivial. So people who do human sciences can very quickly show that there is, beyond the very basic hand-eye coordination and the building up of muscles, there is actually very, very little transfer between, let's say, hockey and golf, for example. That's well, somewhat problematic, obviously, as well in this context. And then learning has to happen in real time, on a real system, and that means we have to deal with computation limits, communication limits, and energy limitations pretty much all the time. So with other words, learning, despite that now finally, thanks to all the breakthroughs on computer games and all the other computer vision, natural language processing, all the other domains, we actually still don't have learning as a straightforward answer in robot learning. And by the way, I don't know, this video probably did not play. I don't know why. Oh, it did play. This here just shows you how expensive data is. That was an example from my PhD. It required getting up several thousand times, putting that stupid ball back onto this pole. This is called T-ball. This is how American kids learn how to hit a baseball. I still feel the back pain, so you see how expensive data is. So learning alone is not the straightforward answer. So what do we require? Well, from my perspective, we really do require that we put in sufficient prior knowledge so that we can actually learn from the real system in real time from very limited data. And the key ingredient for that is that we put in the right inductive bias. So what's an inductive bias? Well, an inductive bias allows a learning algorithm to prioritize one solution or interpretation over another, independent of the observed data. Inductive biases can express assumptions about either the data generating process or the space of solutions. All big questions are, therefore, well, what inductive biases does robotics offer, and how can we actually use them to improve robot learning? And therefore, the remainder of this talk has a straightforward outline. I'll be talking about 6 of the many inductive biases we found, and well, then finally give you a quick summary. Let's start with a simple one. When I started my first paper on reinforcement learning, it took me a long time to finish it. It was 2 years over reinforcement learning, and a lot of people told me, don't do reinforcement learning. Imitation learning is always easier than reinforcement learning. Obviously, they're right. It's always easier to imitate. In fact, we human beings are even made to imitate. We have this as a bootloader, just like a computer has a bootloader and the BIOS. We have this bootloader that we are made to imitate so that we can get started in it. This is also why we do so many foolish things, just because other people do foolish things, because, well, our bootloader kind of makes us acquire these programs. So imitation learning is always easier, and it's obviously true. If you take the simplest objective of imitation learning, the one where you say, well, there is a distribution Q over the states and actions you've observed, and you want to reproduce this with your policy pi, which is a conditional distribution of actions given the states, and then some resulting state distribution, you can directly derive a series of behavioral cloning algorithms from this objective and get imitation learning algorithms. And in fact, we know this not since yesterday, but the first imitation learning algorithms date back to the 1960s, where people like Mitchie and Chambers and many others already in Edinburgh, and I think also in Bristol, proposed the first imitation learning methods. And in robot learning, they got really pretty promoted in the 90s. So in other words, imitation learning straightforward, but imitation learning already with prior knowledge is not such a novel thing. In fact, formulating this objective together with the constraints, kind of model-based behavioral cloning, did not happen up to the early 2010s with, for example, the work of Peter Englert or Abdeslam Boularias. The dual to that has been really popularized by Peter Abiel, Brian Siebert, and many others, because the dual of that kind of a problem is actually, as we know today, just the inverse reinforcement learning problem. And you can solve this also for minimal physics, which gives you nice policy representations. But really, really important to notice that this dual or inverse reinforcement is actually harder than the original primal. So we are actually solving the wrong problem when we're trying to do inverse reinforcement learning, where we have quadratically many constraints instead of linearly many, which we would have in the primal. We've used imitation many times. This is just an example of Sebastian Gomez-Gonzalez work, one of my PhD students, who managed to learn table tennis forehands completely from data, and by just having 6 successful demonstrations and learning the hand-eye coordination, the computer vision, and everything in one go there, and achieving a 99% success rate against the ball gun over the table. But if imitation learning was always sufficient, well, we all could go home from primary school with a PhD, right? Just to imitate the teacher. Clearly, we need reinforcement learning, and this really gotta make us feel awkward, because when you look at the RL objective, you recognize the objective does not include data. There's no notion of data in the objective, and adding the constraints, as we did before, does also not introduce data. In fact, all the famous ancient algorithms like Q-learning, saucer, and so on, they're actually quite artificial when you think about them. They really artificially bring in the data by pretending that the data is representative of the last policy, and then we have basically, we take the average argument, or we take the policy grading algorithm, and pretend we're so close to the policy, so that whatever we fit to it, that in terms of parameter changes, again, can be derived from the data. But in both cases, we've actually done a very, very artificial pattern. And well, we most of the time we don't use this primal, but we actually again use this this dual. We use the primal, or sometimes decode it even by the Bellman equation. But it actually turns out that already the old Markov decision process literature said that this primal is harder than the dual. So we should actually stay with the dual up there if we want to get efficient algorithms. Most importantly, there is no natural notion of data in here. Now, it turns out that this should actually give us our first bias, since we should clearly stay close to our training data instead of artificially bringing it into the problem. And for that, we found, well, one really, really helpful insight, which has been behind most of our algorithms, and that is that we take the reinforcement learning problem and the imitation learning problem, we eliminate all the parts which are redundant, move the imitation learning objective into the constraints, and voila, we actually have a new problem, and one which is even guaranteed to be convex if you have, well, linear policy assumptions, or more general, well, you can more generally also use it in a nonlinear context. Now, this yielded a ton of different algorithms and has a ton of connections to other algorithms. Since you can compute analytic solutions for linear policies, you obtain the mellow and softmax formulations, and all of the modern things like entropy regularization, SAC, and so on. They're just instantiations of it. Similarly, if you want to do approximations, you find things like natural policy gradients, net-vector critic, or TRPO, actually turn out to be approximations of this program. So it's actually quite fundamental. For our learning algorithms, this is actually still the state of the art. Here you see Kai Plöger Kai did actually his master's thesis is on juggling. And well, here you see the one-handed juggling of the robot and Kai juggling right behind it. And it, well, learned from relatively little time. The initial solution could directly juggle for 30+ minutes. I think the maximum Kai has run it on the robot. The wear and tear at some point gets to the robot is 2.5 hours without mistake. And it really works extremely reliable. This here shows you the learning process. Again, the 30+ was in the very beginning. And here you see the different episodes always used for policy update. So episode means here actually the policy updates. So these are the episodes of policy update 3. And with altogether 400 rollouts of 56 minutes of robot experience, he managed to learn this one-handed juggling. Now, being in
What sensors did he use?
he has cameras looking onto the ball. So these are, you notice these balls have reflective tape, so that's relatively simple to detect. And there are, I think, 12 cameras looking onto that space. I don't know how many can actually see it. They can see everything. We also have he also has later versions where he tracks the hand as well. Here he uses the joint encoders in addition to it. Sorry, the motor side joint encoders as in addition. So Kai showed me this on a Friday. You should never show something to a professor on a Friday. That's generally a bad idea for any PhD student. So I was happy and I made a comment and said, but you're really, really gonna show me how now 2 robots juggle together. I didn't expect them to do anything about that. I expected them to submit his master's thesis and then be done with it. Instead, he calls me into the lab on Monday and he showed me this. Same algorithm, 3 balls. He apologized. It's only 3 balls juggling with 2 arms, since that's actually easier for the robots. He had tried to do 5 balls right away. Turned out that was with the hardware of the time, that was the hardware of the time limitation. Now, currently he works mainly in simulation, but in simulation he has broken, he has basically reached the physical limit, which is 17 balls at some point because of the parabola in the middle. At some of the time point, the balls start colliding and you simply can't go beyond that physical limit. Plus you have also obviously the ceiling height and the maximum accelerations and so on, which play a role there. So the physical limit is at 17 balls. He manages to reach it. Now my big request from him is to go from simulation again to the real robot with that, of course. The 17 balls in our lab, by the way, won't be possible. The ceiling height is kind of like here, so we would have to destroy the building above us. But talk to my president if you want.
Can you explain now how you get, before you made an argument that the data is not, or you cannot get the data in? How do you get, so where's the data now with this new formulation?
So with the new formulation, we directly have this constraint on the distribution. And by not allowing a big data loss, we always have the data automatically in all the equations. In all the updates, it automatically appears.
Alrighty, so first inductive bias, stay close to your training data. Second one, well, again, starts with the one mod. And well, robot movement, well, actually human movement is supposedly either composed out of strokes or rhythmic behavior. Juggling was a beautiful example of rhythmic behavior. And robot movement should obviously be the same. So we try to actually now really deal with very, very large trajectories. What you see there is one large gray trajectory of, I don't know, several, probably 10 or 15 minutes of robot time. And we don't want to do any pre-processing, any resets in there, and just deal with that for imitation. So this is table tennis data, but we also have data, we also use data from manipulation and many other tasks that way. So we're going to feed this without pre-processing right into one learning system. And in order to create modular particular libraries of behavior or of sub policy. And for that, well, we take this big data, we over-segment it, we build a library with an EM-like algorithm, and afterwards get a distribution over trajectories, over possible trajectories. And with that, directly the accompanying policies as distribution over actions given the states. So that gives us the second inductive bias that we want to use modular policy structure for composition. Of course, in order to use these policies, well, we need to then, require also several layers, since we need a gating network which decides which modules to use, and we need the actual sub-policies which activate the behavior. If you take the program from before, well, we can, of course, do one thing. We can do a naive extension. We just introduce an O as option, so Rich Sutton would put it in there, and add one more red policy into it. We could be done. At least that was our initial thought, and our initial thought actually worked quite well. Here you see table tennis with several different strokes. In this case, it uses cameras both at the ball. So there are 4 cameras from 4 different directions which see the whole table and basically can track the ball. But there are also 3 cameras looking at the human being and trying to predict from the human being's movements before the human has even hit the ball, whether it's going to be a forehand, a backhand, and or some other location which the human wants to play to. And this is actually quite crucial because in the end, our robot doesn't have the accelerations of a human being. So then deciding between a forehand or a backhand has actually to happen before the human has hit the ball or the human has to play a really slow. And well, in this case, the naive extension worked. Well, why did it work? Because a forehand is in the end very different from backhand and relatively easy with the movement to identify even from like the few pixels in the fast cameras which we use in the setup. They're VGA quality, so you can, and they're really bad cameras. So even from that computer vision data, you can identify whether it's a forehand or backhand with the learning algorithm.
Sorry.
Yes.
So this is a redundant, the manipulator.
It's the 7 degrees of freedom Barrett WEM arm.
I'm sorry, very naive question.
Mhm.
How do you solve the industry maps?
We don't.
You don't, okay.
We learn the policy which directly creates striking movements, and which has another learning module which transfers which gives hyperparameters to that model so that it adapts.
So you are always in controlling the robot in joint space.
Yes, and in fact, even for human table tennis, you can show that humans do not solve the inverse kinematic form all the time. That would be very awkward movements if they did. For writing, on the other hand, you solve the inverse kinematics problem, for example, all the time. This is why writing with your foot, your mouth, or your hand gives you the same trajectories, while high-speed movements in sports are typically, especially in striking motions, they're really learned in muscle space, and they were learned in a way that you get the maximum performance out of it, which is the reason why in figuring out actually the best possible policy is actually the reason why it's so awkward to learn a sport like tennis. So you initially do movements you don't directly think of straightforward. Because when you try just straightforward things, you typically as a human being too slow.
So in this case, how do you take the working space in program?
So we initially move the robot by imitation running around, and then we let it play against the ball gun, and then we let it play against the team.
Okay. So the only working space he knows about is the ball.
It's arms movement.
Yeah. Yes. Yeah. There is no such notion of the tabletop and things like this.
No, there's only an emergency stop if you fix the table accidentally.
Okay.
We've moved the table also so far away that it barely ever could touch it. So we never showed a trajectory so it should touch it. So just staying close enough to the training data, that's not becoming a problem. You could give it a reward for staying away from the table, which would probably be a smart move, but I don't remember that we ever did that. Yes.
When you use imitation learning to learn first, and then you learn with self-play, you don't suffer from a distributional shift because of the data.
Oh, you unlearn much of the imitation learning. So in fact, we had initial players which were learning peak of imitation learning. They never reached more than 60% success rate against the ball gun. And they have to cover the whole table. If you specialize them, then you can, but they only have a region of the table, then they can reach 99 something percent, which Sebastian did. But then you have to really, well, if you take just the forehands, if you have forehands and backhands, then it drops very rapidly. One thing that it always learns from then after doing reinforcement learning, based on imitation, is that it removes the very high acceleration humans can create, because with our muscles we just have an actuator which is very suited for acceleration, and it replaces it by very long high velocity pieces, which are very hard for us humans to do accurately, which is the reason why there's actually a huge distributional shift. And yeah, I'll tell you a little bit more later there.
But first, let's get to the problems of naivety. So I told you we naively extend our program. And you can find problems like tetherball where this kind of behavior happens. So what does this kind of behavior show? Well, it basically shows how our system has learned not to specialize. It has learned two primitives, and each of these primitives is really good, but they try to solve two problems at once. In this case, this is it's a problem where you have two really good solutions, and by not specializing, well, your system will just remain average or mediocre. And it turns out that there we need to have one additional constraint in order to force limited responsibility to the system by constraining the entropy stored in the gating network. In this case, it specializes, and in fact, we can show that we get a higher performance and at the same time a more natural approach, or a more principled approach actually, to reduce the number of primitives or options in the system. So that gives us the second inductive bias, how we should use modular policy structure for composition. Now let's go for the next two. And the next two, well, they're an experience all of us roboticists make, right? Models can be very, very powerful, but errors in models are typically exploited by reinforcement learning.
To me, this happened very drastically. When I was a postdoc, I just got my own lab at Max Planck, and my director said, like, here, Jan, you have 150K euros, which was way more back then than it is now, more like $500,000 now. Buy yourself a beautiful robot, impress me. Obviously, I want to impress him. So I bought a very random, high-speed, modified version. Nobody else had the world in that form. And I really wanted to impress him, so I directly said, okay, I want to be faster, it's got to be model-based reinforcement learning. Trained the policy first on a model, we had learned from data, we trained it, worked on the simulator quite beautifully, and I was super happy and also a little bit cocky. And I directly ran it on the robot where it did right into the joint limits. Instead of going to him and saying to him, okay, I gotta impress you now, I want to say, please, can you give me another 10K euros so that I can get a robot in repair? I think it was nice, didn't fire me or anything, but allowed me to continue. But I looked into the data, and it was really quite fascinating because the model was super accurate. It was accurate up to a 0.25% of the normalized mean spread error after all. But sometimes in the model, you would have, due to all the regularization effects, you would have the wrong incline. So one higher derivative, which you never look at, had the wrong incline, and the system figured out the reinforcement learning algorithm figured out, oh, there is an energy pump here, and I can just get free energy if I use these artifacts. Of course, these artifacts were not real, right? So the system created a behavior for something which was not real and therefore turned unstable.
So this is one of the many examples. There's way more if you talk to Chris Atkinson or Stefan Schaal or many of the very, very old people, of the last generation before. They will all tell you about examples they've seen where where reinforcement learning algorithm has exploited the errors in the model. Now we tried therefore to really figure out the space of the space of models and how to get physically consistent ways of reinforcement learning to work. So for example, how we could take the Newton-Euler assumptions, replace some parts by basically gray box models, and then learn on these kind of models. And this shows you how different this can be. This here is just a physical model with classical physics, so the so-called nominal model. This here is one with a feed-forward neural network. This here is one with an LSTM. And this here is one where, well, basic physics was used in a gray box version. And well, what you see here is that you get 90% success rate of the bottom the cut behavior, learned completely on the model from 4 minutes of robot data. And at the same time, you get even the ability to generalize to different string lengths with a 60% success rate. So it's actually quite a good performance. And neither the white box model of classical physics nor the completely black box models of LSTMs and feed-forward neural networks accomplishes that. Now, Michael actually went on to figure out the complete space of algorithms between black box and, well, the white box models from classical model engineering and, well, from adaptive control and system identification. And generalizing Newton-Euler to the gray box is one part. You can go one step further and go for Lagrangian physics and do that in a gray box fashion. And when you do that, you actually get, well, very flexible systems, and they, well, work actually you can learn a lot of things really, really well there. Now, Michael proposed the deep Lagrangian networks, and we thought, like, okay, he's done with that problem. We showed this. We did not expect that what he kicked off with that there would be afterwards people coming along saying, oh, I have the Hamiltonian neural networks, the Newtonian neural networks, and there were people writing suddenly PhD theses all over. But when Michael actually used this on a real robot, everybody else was just using a pendulum or a single point mass. But it's really been a flurry of algorithms now around this kind of approach. So, third, inductive bias. If you use models, please do use physically consistent models. Everything else in learning will fail, and will learn physically consistent models by employing the right kind of gray box approaches. But there's something more fundamental about using models and simulators for learning, something which is even more fundamentally wrong. And Fabio really figured that out, which he called the simulation optimization bias, or SOB, where you basically see that the true optimal solution, which you would learn from data on the real system, is actually guaranteed to underestimate the optimal solution for samples when you do sufficiently many rollouts. So with other words, we have a guarantee that we are going to overestimate, due to small errors, we're going to overestimate the true optimal solution, which would be here, and therefore going to have the simulation optimization bias. And so we're guaranteed to be wrong. And well, Fabio really tried to explore this big time. He used this ball balancer. Now, this is not just a ball typically, but it's actually ball filled with all kinds of stuff you could find. So you put anything in there from paper clips, sand, hydraulics oil, which was a really big mess, to anything you could find in there. and the ball is also not in a perfect shape anymore. And you would have it learn policies which work well across many simulated environments. So paper clips have very weird dynamics, for example. And then you use the same approach also for card pull and well, very different pulls. That's in order to learn well policies which are working with a simulation optimization bias. So that brings me to the fourth inductive bias, and that is that you should control your optimization bias. But that is really crucial whenever you're not learning directly on the real system. I start to see some more tired faces, so stay with me. It's just 2 more biases, and then we're going to be done. So let me start with, again, a bon mot. That bon mot is that the fastest way to destroy your robot system is to do exploration. I think anybody who's done reinforcement learning on a real system knows that part very painfully. And for that reason, we do need safe exploration. And for that, reinforcement learning people, or generally robot learning people, too frequently forget that classical robotics hit its problems, not in the reward function, but in the constraints. So by hiding that in the constraint, we make our problem very different. And so when you look at people running at the moment in simulation, some of the big things doing giant clusters, you look at their reward functions are often several pages long. In fact, I think I've seen beautiful talks by Leslie Kapling or Tomas Lorenzo Perez, where they made fun about these reward functions because they're so complex that you could write like the whole program for the robot in the time where you figure out the reward function for it. So we clearly just have moved the problem in this case to the wrong location, and in most cases, just to ensure safety during exploration. If you do this right for robotics, we need to have the right kind of constraints. And my PhD student Puse, he went to figure this out, and he suggested we should use our constraint to direct our exploration. So for that, he basically says we have to figure out the constraint manifold. And on the constraint manifold, we determine the basis of the tangent space. And then we make sure that all exploration happens in the tangent space, and that we use curvature correction and error correction to remain on that constraint manifold. So where does this constraint manifold come from?
Well, we found 3 ways. One is obviously easy, human insight, works most of the time. Another one is you can teach it very well by mutation learning, because most constraints are geometric, so they're relatively easy to learn with a standard supervised learning technique. That also works quite well. And then we can also, of course, do the most dangerous part. You can actively let the robot search for the constraint and do this in a policy iteration style. This is the most dangerous one because once in a while you do still break the robot in that case. Now this here shows you a case where the robot was given the constraints by imitation learning, and the only thing it knows is that there's a constraint on being on the table. And then it does motor babbling. And within 100 epochs, it has learned very nice ways of shooting the book. And they have learned, Puse and also Davide have learned an amazing number of behaviors with that algorithm. So you see smashes, you see cuts, you see repels, you see a preparation of the ball for a shoot. And then this one I find the most impressive, because for this one here, when you look at it, I think very few of us can do this, that they hit the hook to the side with full speed and then hit it again right into the goal out of that. At least very few of us computer scientists can do it, maybe some sports people.
So that brings me to my last inductive bias. And with the last one, you guys probably know even better than I do, since you have the mountains right next door. But the first thing you hear from a skiing teacher or from a surfing instructor or even from a tennis teacher is, let your body go over the floor. There's this magic where you gotta trust your body, you gotta follow your body, and then magically you will get down the bump piece, the black bump piece, which looks super dangerous. And there's some truth in that, right? We follow our mechanics. We use our mechanics for exploration. And therefore, we decided we actually need to build robots in a way that they become useful for learning, but are despised by the classical control engineer. So what we ended up doing is that we took very strong actuators and very small moving masses, and we put them in an antagonistic setup so that we have, well, compliance, we have fewer damages for the robot by itself, but at the same time, something which is actually really quite an evil system. Because it's really not that straightforward to work with. So we really build it for performance and at the same time for learning and not for feedback control. And we had a very famous classical control engineer in our lab. He looked at us and said, you guys, this system may be a computer scientist's wet dream of the control engineers. And he was totally right. He did not manage to make it work with a classical control engineer. We tried, and we had good control engineering, being master students trying it very hard. But this was built for learning. And now what you see here is actually the actual learning. And because of the way it was built, we started with motor battling, so absolute zero knowledge. And then, well, and in fact, Dieter and Simon decided they can leave the room while the system is learning. They decided they can just leave the camera on, leave the room, record everything which happens. It gets an old ball trajectories from the ball gun, which are, if the robot accidentally hits a simulated the recorded ball, then they would simulate the rest of the ball trajectory. But otherwise it's like a real ball trajectory. And you see that after an hour, it starts to look like actual hitting behaviors. And well, after 14 hours, it actually was playing quite well against the recorded ball gun shoots. And since 14 hours, you can imagine, that means going back home, have a sleep, have a shower, dinner, and then come back, see what the robot is doing. And well, here you see the behavior against the simulated ball. It required a little bit more of additional training to hit the real ball, because hitting it to a location that the racket ball interaction isn't that trivial in practice, unless you do a reflective movement, but that's a very bad one. And well, this is among the best table tennis playing in terms of the just single strikes, which I've seen so far. In fact, Dieter is building now a version 2.0, which looks actually quite a bit more impressive. Sadly, he's done with his PhD, so I'm kind of dropping out of that part.
So basically, what you are showing is you are learning the simulator.
So the real robot arms movements are being used. The recorded real ball trajectory is being used up to the point where the ball hits the racket, if it hits the racket. And then, well, in this case, the rest is being interpolated using a simulator. That's used for the training period. After that, it still requires about 30 minutes of training on the real system. So the only reason why the simulated ball was used here instead of the real one is that it's quite painful to collect balls for 14 hours. Otherwise, you could.
So what is the reward in this case?
In this case, it gets a reward for returning the ball, and B for hitting the ball. So these are the two things
and so it gets a reward. And it's-
Okay, and doesn't know whether whether the ball successfully hit the table.
No, it gets a reward for hitting the ball and one for successfully on the other side of the table.
Oh, okay.
So hitting the ball is actually the harder part for it.
Okay.
Since
So again, you measure this with some cameras that.
Yes.
Okay. That basically you check whether the ball is returned to the right in the right space or something.
yes, that's correct.
Maybe I missed this, where's now the process that you have to follow the flow of the body?
Well, the whole exploration is determined by the muscle-based system. And so it really just tries to initially by wrapping the arm around, by motor to baffling, only the things get excited which actually are excited by putting a random sequence of the body in there. And then basically by always just strengthening the parts where the body does a relatively natural movement, you get it to move in the first place.
Yeah.
So if you were doing any form of structured exploration here, you would actually fail because the system is simply not made for it. So the same, if you had a fully actuated robot, you would do much more structured exploration.
What do you say? What do you mean by muscular robots?
Every degree of freedom has a pair of antagonistic muscles. They are the testopneumatic muscles, relatively bitchy muscles that can create very high accelerations, in which which are very nonlinear springs, so you can give them quite arbitrary dynamics. So you can also create, for example, catapult-like behavior by just having both of them in co-contraction, then releasing one of them, and then this basically gives you one spring, which is really, really strong, and the other one so relaxed that it is like a catapult. And so you can do things which you cannot do with a motor-based system.
Yeah,
At least not with a weak motor-based system.
Does the robot has a wrist or no?
Yes, this one is only 4 degrees of freedom.
Okay.
For table tennis, the official minimum is obviously 5, because that's how many you would need to hit the ball in any direction. But it turns out that 4 are practically quite frequently enough. Again, this may be different if the robot was trying to cover the whole table or something.
Now, next question.
Mhm.
So here the impact of the ball into the is limited or not, right? There is almost no consequences of the impact. So that's maybe one reason why you can train in simulation and then get transferred, I wouldn't say immediately, but nicely to the real life. If you had some feedback into the robot from the impact, then this would cause a problem when transferred.
Probably, but actually it's not even that trivial with the ball being light. So for example, if you kept the spin at a relatively small level, if you turn up the spin, then the sim to real transfer would already be problematic. Because if you have a very, very small error in the spin axis, this can already determine whether it's a forehand or a backhand. That's actually the reason why human players, so one of the reasons why in the earlier part we learned how to predict from the human movement whether it's a forehand or a backhand and which strikes to take, was that human players, yes, are quite capable of putting a spin in there such that you can only decide whether it's a forehand or backhand from the ball trajectory after the ball has hit the table, and most of the spin is out of the movement. So without the spin reduction, it's actually really, really difficult to predict. In fact, even people who study this all their lives, so we talk to Deeptails, that's the Balkan manufacturer in southern Germany, and they basically have managed to accidentally bump into the senior boss of that company, because it's a family-run company for 120 years. For 120 years of physics models, and they basically had precisely our experiences that they said, well, if you have real spin in there, you can throw most of the physics stuff out of the window because you can't measure accurately. You don't get enough frames in order to interpolate on just the Gauss trajectory for any good physics model. So if you get really like you have a 10K camera, then you can start to use them, but not from the few frames you get from a 200 hertz camera, and especially not even from, definitely not from a 60 hertz camera. So
how many cameras?
we have 4 cameras. Each of them has 200 hertz, but most of the time we just use them at 100 hertz because the computer vision module running on a GPU doesn't get the data fast enough into the GPU and out. And so for that reason, most of the time we run our computer vision modules.
So basically, the cameras see the white, the yellow dot. Right?
The cameras see an orange dot. Actually, it's even more complex than a dot. It's more like an ellipse typically because the lighting makes a real difference. Yes. These are industrial cameras, so and we haven't made the problem easy. Making the problem easy would be if we
had painted. Well, here we did make it easy later, but in the earlier versions we didn't make the problem easy, for which we designed the. Let me show you the background there. That was one of my most stupidest decisions, by the way. We decided not to make the problem easy
and have a white background or something because you can make the computer vision easier.
But here, so the 4-camera system is the camera setup is calibrated. So
it's calibrated everything, but
so
you spend 2 PhDs on, I think, on computer vision solutions. It is actually quite hard to do these things in real time, even when they can.
I understand that. I mean, it made me think of old-fashioned motion capture systems where you have markers. So the ball is like a marker, right? So you can use this.
We tried that. So we used the Vicon setup. We coded. We had a professional company code the ball with the Vicon color. Humans with a hell of a lot of acceleration can actually play table tennis with the coded Vicon markers. The coded Vicon marker color coded table tennis balls. It is super straightforward. You're exhausted after we try to understand the reward functions of humans. You could not actually use that with a robot arm. You can't do the accelerations. You would actually.
Yeah, sure. But here, what I mean here, basically, if I understand well, the computer vision part just provides you XYZ as a function of time. Am I correct?
So different versions we've done. Sometimes we've used the raw pixels in some of the pairs we learned. In some we actually did the complete pre-processing, trying to figure out the X and Y and the different cameras, and then do the triangulation. Big problem though is that if you introduce structured lighting, and meaning really good lighting, if you introduce a white background, then the balls actually are balls. Most of the times they're not, because they become ellipses, and small errors actually can easily give you a very, very bad computer vision scenario. That's why we at some point decided to also learn this rather from raw pixels than to use classical computer vision.
Okay, so basically
we've explored the whole space of solutions there.
Yeah, so basically each camera image and passes to a CNN light.
That was the solutions we ended up in the latest version.
Okay. And it
works actually better.
Okay, that's interesting.
And we've worked with really good computer vision people like Christoph Lamberg, for example.
So in that case, it means that you have trained with 4 CNNs, for instance. So
you can do one big one also.
You have the ground truth for the ball.
Yes, you can do it that way. Then you use Vicon markers for the tracking the ball, and that's one way we collect the data there in comprehensive. So we've really explored all the different ways, and the sad part is it's very hard to publish this kind of computer vision work, since only the real-time people are interested in it. That's a very, very small community. So for PhD students, it's not a very great task.
Just the fact, have you tried to look into event-based vision for tracking the balls? So
Okay.
you have a static camera and then make it tracking moving up to 2 feet.
So we wanted to do that, and but we didn't do it back then. We want someone else to try FPGA based because we get higher speed there. Event based would be quite natural. I think now there's so many similar things done by the Zurich people that we think it's not the right problem to work on anymore. In fact, I'm dropping out of table tennis. I've dropped out of table tennis now. I've had enough of it. So also now the competition is really quite bad since for a couple of years now the Google people are doing table tennis, and well, they have research engineers. They don't do work by PhD students, and so if it's just about performance, it's no longer fun for us. So we'd rather than try to explore new problems where there's less competition, hopefully. And also less, the key thing we need in order to become better in table tennis now, we need to do not really research problems anymore, right? It's putting the robot onto better and better linear axis systems so that the robot can slide really fast. Humans do that, we sidestep all the time. We use the same primitives which we know that work all over instead of being nailed to the ceiling. It clearly requires two people working full time just on that kind of system. Making this better and better computer vision work in real time. And I said it already, it's nearly unpublishable. So really bad for a PhD student again. So the limitations in table tennis are not so much on the scientific side.
Maybe if you want to go more towards the computer vision side, maybe you can also have a camera that looks at the opponent.
That's the one thing we did for selecting the parameters, that we watch the opponent, that we
observing
the opponent.
Observing the opponent hand motions. I think it's a basically
this is precisely how we selected the strokes. We decided we did the selection policy be completely based on looking on the opponent, and we learned to completely use the opponent, while the policy which does the strikes itself mostly uses the ball. But yeah, the most, again, there's the tiresome part. You need to have the whole system work against the all the time, so it's not actually fun researching part. We look in various other problems there these days. Okay, but
you were a source of inspiration for the
great. That's the life's purpose. So last inductive bias. Let the natural dynamics of the robot guide your learning process. And with that, I have our conclusion. Use your inductive biases. Here are 6 examples, and thank you for your attention.
Yeah, pretty many questions, but that, I guess, time for a few more.
So you said that because you have a Google competition, so what's next in your lab?
I can't tell you everything, of course. Well, at the moment we like this hierarchy task a lot because it's something where you can where we are in contact with the environment at all times. So we, instead of having only this intermittent contact which you have in table tennis, and so we're currently running a competition there, which is where anybody can partake. So you're highly encouraged. At the moment, there's 14 teams on it. We explored the space first ourselves. Now we want to see what everybody else does, so that it really becomes a community thing, and then hopefully publish a joint paper on it, where we bring a lot of people in and really show the big picture a bit more. We're doing tactile sensing for a very long time, and we figured out a lot of things humans do during tactile sensing, which are quite interesting, and we hope that we bring more of that to real systems. So, so that's kind of important to us. We are also looking a lot into how we can create setups now where we can go out of the room, let the robot learn, do this with one robot, but really look at the horizon of maybe not a child, but a teenager. How fast could a teenager learn this task if he was blindfolded, for example? And just do this completely based on tactile sensing. We try to find equivalence to the Turing test in the robot learning domain. So we can't differ anymore whether it's a human or a robot performing the task. So these kind of problems are at our center at the moment.
Yeah.
Okay. Oh, sorry for being too far away from the microphone. I did not see the chat.
So maybe in all these inductive biases that we discussed, they are very useful when you have like a very maybe physical task. That it does not relate much to human behavior. Maybe it's for thinking or something a little bit, but so in the team we are interested in how like robots discuss with people, and then we are facing like the same problems that you mentioned to motivate inductive bias, but we are facing them with like social.
Yeah.
And it seems that some of the, I mean, I'm not sure that all of these inductive biases actually can be mapped into that. So I don't know if you have any thoughts on that, any thoughts.
Okay. First, I think we should, as a community, really try to figure out all the potential inductive biases that be useful, and then reduce them to the ones which generalize across the most problem domains. I think that is one of our long-term goals. We don't know so much about how we can use them in social behaviors. It's a very, very good question. I think there is a lot. So when I look at tactile sensing, let me give you an example. Do we have anything to hold? Okay. An example. I hold something. My fingers, one of my fingers, two of my hands, or even against two. Let's just grab onto something. No, that's what it gets. No, you're not good at this. But we're typically out of the box cable control. We're just using the same control law. We can even isolate it using the same control law for joint manipulation task, which we would use for our joint manipulation task between our two hands or in our own hand. So it is clearly something where the neuro control hardware has already the policy learned by the human beings behind, for making us use it now collaboratively, just so that you get on that step. And so there must be the same kind of inductive bias for the control policy there, because otherwise you would develop a different policy for the joint manipulation than for the manipulation by ourselves. To be clear. So I find this is a very, very strong argument for the this generalization happens at the bias level, not at the task level.
So for me, it's also that maybe in the future we need kind of a meta algorithm that looks at the problem and tells you what inductive bias would be nice to do in this problem.
Yes, I agree. That is precisely what we should do.
That's fun. And again for the talk.
Thank you.
We'll be around this afternoon again. We need the robotics and the AI workshop tonight in our labs. So Thanks.